Yeah, Assalamualaikum and a very good afternoon to all. Okay, right. So I'm glad to see you guys again. So I hope you guys are safe and healthy, and please take care of yourself during these difficult times. Okay, right. As you guys know, that the numbers of COVID-19 cases have risen significantly for the last few days. Okay, so I hope you guys all take care of yourself. Okay, right. So our lecture today will be on introduction to vapor liquid equilibriums. Okay. Okay. So what is the objective of our lecture today? Okay. The first will be to discuss the nature of equilibriums and the two rules that give the numbers of independent variables required to determine the equilibrium state. And also a qualitative discussions of vapor liquid phase behavior. And the third will be the introductions of the two simplest formulations that allow calculations of temperature, pressure, phase compositions for systems in vapor liquid equilibriums, okay, particularly Raoult's law and Henry's law, and the modifications of Raoult's law for the fourth objectives, and also the calculations based on equilibriums, ratios, or K values which are to be considered. Okay? Okay, so what is equilibrium? Equilibrium means that it's a static condition where there's no changes. Means that, the rate of, let's say we have two phase, okay, right? We have liquid phase, okay, at the bottom, and also the vapor phase at the top, okay, right? So when it is in equilibriums, that the vapor phase will condense and turn into liquid, and then the liquid phase, it will evaporate, turn into vapor, okay? So this rate, basically, the same rate. Okay, it seems that there's no changes in evaporations or in terms of condensations, but somehow it's actually the process is still happen. Just that the rate of condensations, right, from vapor to liquid is the same rate as from liquid to vapor. Okay, that is what we call as equilibrium. So in another sense, that when a system achieve equilibriums, the process doesn't stop. Okay, right? There's a still process going on, just that the rate are the same. Okay, this is what it says here. It means that at the macroscopic level, the conditions are not static. Well, they still move, okay, but process, but somehow the rate are the same. So you observe, it seems that the process is static. Okay, the measures of compositions. Okay, I think you guys have covered this in your physical chemistry. Okay, right, for mass, okay, we have three most common measure of composition, which are the mass fractions, mole fractions, and molar concentrations. Okay, the mass or mole fraction is defined as the ratio of the mass or number of moles of a particular chemical species in a mixture of solutions to the total mass or number of mole of mixture of solutions. Okay, so normally we denote that as xi here. Okay, I indicate the species, x is the fractions. Okay, right? So this is the molar mass. Let's say we have molar mass for the species I, and this is the total mass. Okay, right? And the dot here indicate that is the flow. Okay, red or the molar mass. Or we can also use mole instead, okay, which is denoted by n, still the same. Okay, right? This is the number of mole of that species I, and this is the number of mole rate or number of mole at species I, and this is the total rate. Okay, so for molar concentrations, we can divide it with the, okay, right? This is the molar, what is this now? Mass, or it's a mass or the mole fractions, and we divide it into volumes. Okay, right? So we denote it as C for species I. Okay, right? Species I. Okay, this is the molar mass or molar fraction of species I at certain volumes. Okay, per volumes. Or if you see in the flow rates, then we can denote as a mole. Okay, now it's a dot at the top here. Okay, this dot indicate it is a flow rate. Okay, right? And divide into the this amount of a mole per time to the flow rate. Okay, now we see the volumetric rate. Okay, and for the molecular mole fractions together of a mixture, we can do the sum here if we know the mole fractions and the of certain species to the molecular weight of that species. Okay, the first rule, Durham theorems, okay. For intensive state, I hope that you guys still remember what does intensive state means. Means that the state doesn't change even though the amount or the composition, the mass of the species changes. Right? So, for example, what is the intensive state? The good example will be the temperature. If a big rock or a small rock, when it's going to have the same temperature, and also density doesn't change also. Yeah. Okay, that is the intensive state, and the extensive state means that it depends on the mass. Okay. Okay. Okay, the intensive state of PVT, okay, pressure, volume, temperature system containing n chemical species and pi phases in equilibrium is categorized by the intensive variable temperature, pressure, and n minus 1 number of mole fraction on each phases. Okay, right? So the number of these phases rule is 2 plus n minus 1 pi. Okay, right? Or we can write down into this form here. 2 minus pi plus n, where 2 is a constant, number 2, okay, right? And then pi is the number of phase and n is the number of species. Okay, right? Okay, right? So the Durham theorems, okay, stated as follow. For any closed system formally initially, for any closed system formed initially from given masses of prescribed chemical species, the equilibrium state is completely determined when only two independent variables are fixed. Okay, so what does it mean? It means that if you want to know the equilibrium state, you need to know at least two independent variables. Like for example, for air, okay, right? Or maybe a mixture of ice and water, for examples. Okay, so you need to know one, maybe temperature and pressure. Or you can use pressure and volume, or pressure and volume, at least two states. So you cannot specify the state of a mass or a species, but just one. Like for example, mixture of ice and water, and then you tell it the temperature is 100 degrees Celsius. It's not enough, because for water at 100 degrees Celsius, if the pressure is very high, right? If the pressure is very high, even though 100 degrees Celsius, we suppose it to be in vapor form, but somehow it can be in liquid form. Okay. But if let's say the pressure at 100 degrees Celsius is very low, then it can become superheated pressure, superheated vapor. Okay. Okay. So we need two actually. For 100 degrees Celsius, we need to know what is the temperature. I'm sorry, 100 degrees Celsius, we need to know what is the pressure. So if let's say the pressure is at 1 atm, then we know, right? 2, right? So we know that 100 degrees Celsius and 1 atm means that water will be in what state? Vapor, right? Boiling water. If it's 100 and 1.5 atm, higher pressure, isn't it? So we know that the water is in liquid state. If the pressure is 100 degrees Celsius and the pressure is 0.7 atm, so means that very low pressure, that it is in vapor form. Okay, so that's what it says here in Durham theorems. Okay, I'll move on. Qualitative behavior. Okay, vapor liquid equilibrium, or sometimes we call it as VLE, is the state of coexistence of liquid and vapor phases. Okay, right? Just like you boil water. Okay, right? At 100 degrees Celsius, at 1 atm, you put the water in a kettles. You start to boil it. There will be some water in liquid form, right? And then some will be in vapor form. Okay, that is called vapor liquid equilibriums. Okay, these two depends on the three things just now: pressure, vapor, and temperature. If you maintain two, or at least two or one, and you vary another one, then the directions of either evaporation or condensation will change. Okay. In this qualitative discussion, we limit consideration of system comprises of two chemical species only. Okay, right? So it will be 1 and 2. Okay, we name the species 1 and 2. Okay, why we only have 2? Because you have 3, it will be more complicated. So for beginners, just 1 and 2. Because the system of greater complexity cannot be adequately represented by graphically. Okay, so it will be more complicated. Okay, when n is equal to 2 and the first rule become f equal to 4 minus pi. Okay, right? Why? Because of number of species is 2. So 2 previous graph here. Right? 2 minus pi plus 2. So that's 4. Right? And because there must be at least one phase. Okay, the maximum number of phase rule variables must be specified to fix the intensity state of a system, which is 3. So 4, and then you have only one phase, then you need 3. Okay, right? Intensive state of property. So normally it's pressure, temperature, and mole or volume. Okay, right? If you know it. So all the equilibrium states of the system can therefore be presented in three-dimensional pressure, temperature, and composition space. Okay, right? Within this space, the state of pair of phases coexisting at equilibrium, F equal to 4 minus 2 should be 2, right? You know just now 2. If you have two phases, because pi is 2. A schematic three-dimensional diagram illustrating this surface for VLE is shown in figure 1. Okay, this is for 1. Okay, right? Okay, let's read it. This is a bit, you have to think, right? Imagine. Okay, right? This is a bit complicated. Okay, right. So equilibrium state of saturated vapor and saturated liquid for species 1. Okay, species 1 is here. Okay, over here, when it's 0, means that species 1 is 0. It's not existed, right? And as the percentage of the species increase and the fraction become 1. So species 1 will be 1. Okay, right? So when species 1 is 0, then species 2 will be pure species, right? Okay, over here, species 2 will be 0. Okay, right? So in the middle here, if we're in the middle here, then both species will be 50%. Got it? Okay, so if I come here, I got 0.3. What does it mean? Means that it's a 30% of species 1, and then 70% is species 2. Okay? Okay, right. So from here, we can see that species 1 is lighter or more volatile. How we know that? Okay, very easy. So you look at number 1 here. 1 here means that it's a pure species 1, and it have a much lower line than this. Okay, this is a pure species 2. So when the pressure means that it is at a lighter, the pressure is lower, right? So means it's more volatile than species 2. Okay, right. Under the surface containing the saturated vapor pressure, it is Pt equal to Y1 surface. Okay, below this surface here, okay, over here, okay, right? Why this surface here? This is the line of bubble point. Is it bubble point? Dew point. I'm sorry, dew point. Because this at much lower pressure, right? Species 1 is in what form? Vapor form. Okay, right? So as the pressure increase there, then you got to see some condensations or dew points. As the pressure go higher, then all of these point will turn into vapor. No, I'm sorry, liquid. Can I? So at this point here, is 0, we don't have any species 1. So all the species 1 is pure species is here. Okay, all these are in because when it's a pure species, you only have one form. Okay, right? But when you have the mixture, then you can have this. Okay, right? So the line here indicate dew points, and this line on the top here is the bubble point. So above this line are liquid, and below this line are vapor, and this is the mixture of vapor and liquid. Okay. Okay, this surface intersect along with R. Where is R? R, K, A, C. I'm sorry. Okay. R, okay. R, K A okay. RKAC1. This should be C1. Can I? Okay, this line indicate a pure species. Okay, right? It's pure species for species 1. And U, B, H, and C2 represent the pure species 2. Okay, okay, right. The critical points are, over here. Okay, remember what's the critical point? Where liquid and vapor exist together and we cannot differentiate that. Okay, right? Remember the hills? Okay, we have the hills and the top there, that's the critical points. Okay, right? So we cannot distinguish between vapor and also liquid. Okay, right? Okay, so the critical point, this is species 1 and this species 2, and this is the line here. You can see the curve here. Okay, this is the locations of the locus for critical points. And the sub-liquid regions lie above the surface. Okay, above the surface here is in liquid form, right? Subcool or compressed liquid. And the superheated vapor region lies below the surface here, down here. And I already explained it to you. And L is the bubble point. Okay, L, this is L here, bubble point. Okay, it is on the surface, on the surface. That is all the bubble point, right? And then at the bottom there, that is the dew point. Okay. Okay, so the bottom surface is the dew point. Okay. A vertical plane perpendicular to the temperature exists is outlined as, okay, we look at here, perpendicular, okay, right? Vertical. A, E, B, B, L, A. Okay, so you got a curve there, somewhere there. That's indicate what? Constant temperature. Okay. All right. So you can see this line here, K. Okay, you cut it horizontally. K, J, I, H, L, K. That is constant pressure. Okay. So if we cut that for temperature, okay, from this temperature, constant temperature, okay, we can get this, okay, from B to A. Okay, look at that. B to A at constant temperature, and then we move again, cut it again vertically, yeah, for constant temperature, and we will get this. We found that it is, and then we encounter a critical point there, okay, right? Okay, right? And then this is temperature A, B, and D, okay, right? So toward the end, because of the here, when you cut it, it cut over here vertically. Okay, if we cut it horizontally at constant pressure, okay, right? So you can see this is what happened here. Okay, at this point here, it is an island. Okay, right? Because we have two critical points. Okay. Okay, right? So this critical point, we can have a locus here, locus of the critical point. Where on the top here, what you call that line here, bubble line, isn't it? Right? Bubble line, and then this is the dew point, right? Line. Okay, so this is a saturated bubble line, okay, and then the dashed line is the saturated vapor line. Okay, so if we cut it across P versus T, okay, let's go back how to cut it across. Okay, over here, let's say we cut it in the middle here. Okay, got the middle there. Okay, right? Okay, from here at constant. Okay, at constant. Okay, I forgot to mention to you that, can I? So we denote this as X1, Y1. Okay, X1 is in liquid form and Y1 is in vapor form. Okay, so we have this value here. Okay, so this is Y1. Okay, right? So this will be in compositions. Okay. Okay. Okay, right. So if we have that, okay, if we got it from B to A, B to D, okay, where is the B to D? Okay, from B here to D, right? All right, you got B to D there. What will happen is that initially the pressure is very high. When we reduce the pressure at constant pressure, what we will see. Initially, we have a lot of liquid, saturated liquid, 100% liquid, isn't it? Now, when you reduce the pressure, then you got to see a bit of bubble forming. Until it reach D, when all the bubble turn, all the liquid turn into bubbles. But somehow, on the right of a critical point, let's say from F to H here. Let's see, what is it in there? Okay, F to where is H? So what I'm about to see here, but it doesn't really matter. Oh, there. F to H. Okay. 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 F to H here. Initially, this is a saturated vapor line. So it means that the species is in vapor form. All right. So when we reduce the pressure, what we will see, right? We will see that some liquid have been formed. We reduce it again, liquid being formed. Okay, at G is the point where we witness there's the most liquid have been formed together with the vapor. And we still reduce the pressure again, we see that the liquid vaporize again into vapor until at H, all the liquid disappear. This is what we call as retrograde condensation, where initially by reducing the pressure, we notice liquid have been formed, and then reduce it again, liquid start to disappear, and toward the end, it's all in vapor form. Okay, that is called retrograde condensations. And for this curve, we have two types. Okay, right? The maximum pressure. Okay, see here. I point C here, and then we have the maximum temperature. Okay, MT. Okay, it's not just one spot. Okay. All right, for our in the phase diagram we draw, right? Remember the hills, we only have one uh, maximum pressure and temperature is at the same point. Okay. Okay, a PT diagram for ethyls and heptane. Okay, for this is very easy. Okay, if you look at ethane, we denote species as species 1. Okay, and then heptane as species 2. If you notice that if we have a different concentrations, then we will have different critical points. Like for example, here this is when what is it? Ethane, right? At 100%. Okay, right? So pure species ethane started here, and this is the dot line is the critical point for the mixture. And toward the end, here is when the heptane is pure species, means that there's no ethane. So you can see here, different mole concentration of ethane will give a different critical point. Okay. Okay, so this is for mole fraction ethane in vapor and mole fraction ethane in liquid. Okay, the point here, A here indicate the highest temperature. Okay, right? This is for the compositions of 77 mole percent of ethane, and the pressure is about 1,239 psia. Okay, we can go back to figure 10.5. Okay, so 77%. So it is basically this line here. Okay, I'm sorry, this line. This at the 8.7 is line. So this is the maximum. Okay, so means that if you want to have the highest pressure, okay, so we need to put in 88.7% ethane, and the rest is heptane. Okay, so that you get the highest pressure. Okay. And then for different kind of system, this for methanol and benzene, you can see that it does not follow the same behavior as previous graph for ethane and heptane, can I? Because the two are very dissimilar. It's not the same. So it provides very weird combinations. Okay. So this shows that over here, it behaves differently, can I? So it curves back again. Yeah. So this shows that, you know, how difficult it can be to predict phase behavior for species so dissimilar as in this example, methanol and benzene. If a methanol and ethanol, so we're very close, similar to each other. Okay, in this figure 10.8, it shows the tetrahydrofluorans, okay, so species 1, and carbon tetrachloride, species 2 at 30 degrees Celsius. Okay, and A here, you can see that, okay, right, this is the pressure for saturated liquid, right? Okay, or bubble point, and this is the dew point here. Okay, both of this line, okay, bubble point will always be above dew point. It cannot be lower, right? Okay, but sometimes it can meet. It can be at the same point. Okay, this is what we call as where a bubble point and dew point exist at the same point. This is what we call as azeotrope. Okay, where azeotrope is where x1 equal to y1, the dew point and the bubble point curve are tangent to the same horizontal line. A boiling liquid of this composition produces a vapor of exactly the same compositions, and the liquid therefore does not change in composition as it is evaporate. No separation of such a constant boiling solution is possible by distillation. So as a chemical engineer, we don't want azeotrope because we cannot split we cannot separate the two species. Okay? So we don't want that. Okay? So if you want to separate the two species, then we cannot be at this composition. Get it? Okay? But we can do it some other compositions. Maybe here, maybe. That will be possible, right? So it will be more tetrafluoride, right? Then carbon tetrachloride and this in this pressure. Then we can separate the two. Okay. For this, it's the same thing here also for C. Okay, right? So you can see that this line here, right? This line here, Px1 will be above the straight line here, and Py1 or the dew point is at the bottom. Okay, right? Okay, so it will be separate here. This also could be possible. Will behave like this, but again, when we have the azeotrope. Okay, this graph here shows for the temperature. So normally, for both, you can see the pressure here and temperature is still the same. Okay, right? Okay, you can see the azeotrope and how does it behave. Okay, so Raoult's law. Okay, by the way. Okay, if you look at this graph, previous graph here, you can see that this 2 point here, right? If there's no azeotrope occurring, you can notice that this two line we have very much close to this straight line here, right? So for modeling, it's very difficult to have a curved line. So we can model it according to this straight line. Okay, this straight line is what we call as Raoult's law. Okay, this is the Raoult's law. Okay, in which we make two assumptions for Raoult's law, that the first phase is an ideal gas, and two, the liquid phase is the ideal solution. Remember that's how we define ideal gas? Ideal gas means that when the molecules, right, is independent, right? It's independent. It's not being influenced by other molecules. Okay, so that is the ideal gas. Okay. And because the independence, that it only can apply for lower to moderate pressure. If the gas or the system is in high pressure, then we cannot apply Raoult's law. Why? Because when the high pressure, the molecule very close to each other, and definitely we cannot assume that the molecules of the gas is independent to each other. Okay, so we cannot. Okay? And the second rules is for ideal solutions. It's implied that the species have to be chemically similar. Okay, right? A mixture of isomers such as auto, meta, and para-silenes conform to very closely to ideal solution behavior. So the mixture adjacent to a number of homologous series, example N-heptane, ethanol, propanol, and benzene and toluene. Okay, the liquid has to be quite similar. So it's like oil and water, you cannot. Okay, right? So it will be very difficult because they're very too dissimilar. Okay, what is Raoult's law? Raoult's law is this equation here. what is it? Y1, what is Y? What is the vapor phase mole fractions? And P is the pressure. Okay, right? And then and Xi is the liquid phase mole fractions time the saturated pressure, right, of your species 1 at the temperature of the system. Okay, P saturated here. Okay, and then I can be any species 1, 2. Okay, like we know your study is only 1 and 2, but it can be many other studies. Okay, so what you can see here, at certain pressure, we can relate the fraction here, okay, which on the left side is the partial pressure of species I, is equal to the saturated pressure times the liquid mole phase fractions of the same species. Okay, okay, from VLE, okay, from this for Rouse law, then we can calculate the things that we want. Now, for example, for bubble pressure, we can calculate Y1. Okay, this is the mole fracture, the vapor mole fracture, and the pressure. But provided that we have the liquid mole fractions and also the temperature and dew point and T and P. Okay, right? So if we have the combination, then we can calculate. Okay. So in each case, the name indicates that the quantity to be calculated either bubble point, like a vapor, or a dew point composition, and either P or T. Okay, so normally in thermodynamic, pressure and temperature is very important, and also the composition in this sense. Okay. One must specify either the liquid phase or the vapor phase composition and either P or T, that's fixing 1 plus N minus 1 or N phase rule. Okay, so we need to consider the N phase rule, the same thing, so that we know what the degrees of freedoms for the VLE or vapor liquid equilibriums. Okay, since that the summation of all the vapor fractions, right, or the species to equal to 1, then this equation here, we put the summation here, right? So we come to 1, and then the summation of liquid. So we can get this equation here. So the pressure can be calculated by using this equation, right? The summations of liquid vapor, liquid mole fractions times the species individual saturated pressure, right? And since that, you know, x2 equal to 1 minus x2, okay, so we have x1 p1 st, right? Saturated p1 plus x2 p2 saturated 2, okay, so the x2 we substitute with this, and then we got this equation. Or we can reverse that, okay? So we got this equation here, but we know this equation is actually what? Okay, the pressure here, right? Okay, P. Okay, P. Okay, oh, okay, it's the same thing. Okay, right? So we know that if we sum all of these liquid mole fractions, it should be equal to 1. Okay, right? So they become 1, and then we can rearrange the equations, then we got this. Got it? So initially we have YIP equal to summation of YIP, right, equal to summation of X1, P1 saturated, but this summation here is equal to 1. So you can cancel that, can I? So we got P, so we got, we can take out the summation of Xi, summation of P1 saturated over Y, summation of Yi, can I? Okay, and then we inverse it to this, okay? Okay, Henry's law. Okay, Henry's law, if you look at the equation here, is very much similar to the Raoult's law, except for the saturated pressure, it been changed into Henry's constant. How we get the Henry's constants is basically from experiments, can I? So the table here shows the Henry constants for various chemicals, right? Acetylene, air, carbon dioxide, carbon monoxide, ethane, ethylene, helium, hydrogens. Okay, so this is, so we just use the constant into the equations. Okay, VLE by modified Raoult's law. Okay, for low to moderate pressure, much more realistic equation for VLE result when the second major Raoult's law assumption is abandoned. The account is taken for deviation from solution ideally in liquid phase. Okay, right? So the okay. Okay, for in liquid phase, okay, right? So we need to include the activity coefficient, which is here gamma. Okay, gamma I is inserted into the Raoult's law. Okay, activity coefficient you will cover it in next semester. Not next semester, in next lecture. Okay, right? When we will be focused more on liquid. Okay, but this is just introduction first. So this activity coefficient is basically a constant, okay, right, to make Raoult's law even more accurate. Remember, like we have PV equal to nRT, right? PV equal to nRT, right? Okay. So this is initially we assume it to be ideal gas, right? PV equal to nRT, but somehow we try to relate it to real gas, then we use PV equal to Z nRT, where Z is a constant to relate ideal gas to real gas. It's the same thing here. Okay, right? So we have a constant there to relate ideal gas to the real gas. You will learn this more later, can I? Where ideal gas, you cannot apply it for everything, but it's the most easiest theory, calculation to be used. So to make life easier, then we add that Z value. Okay, the same thing also for Raoult's number. Okay, activity coefficients are function of temperature and liquid phase composition. Yeah, as I mentioned to you later, you will know it. And normally it's based on experiments. So because these are equal to 1, as I mentioned of vapor equal to 1, then the liquid phase is something 1 equal to that. So we can find what is the pressure there. Or alternatively, that summation of xi is equal to 1, and then we replace that, and then we got this. Okay. So it's the same thing. Just that we modified Raoult's law, try to be more realistic than the actual Raoult's law. VLE from K value correlations, okay. K is basically, remember here, we have 3 lines, means the approximate. It's not exact approximate. You can put it as the ratio of vapor phase or species I to liquid liquid phase in species I. Okay, so this is the K value. For the Raoult's law, okay, we can relate it to be Pi saturated to the pressure and modify just the activity coefficients. Okay, so from this, okay, this for the Raoult's law and this for the modified laws. Okay, right. So we got this equal to 1. Right, because you guys know this, right? One is 1, and then if we sum this, equation 10 10, okay, with this value here into this value there, okay, right? So we got summation of yi over ki should be equal to 1, okay, right? Yeah, because I've already know that because it's a ratio, right? Okay. Okay, 1, or if you put it there, yi xi. Okay, if you put it here, yi xi. Okay, the y cancel, you got summation of xi. Summation of xi is equal to 1. Right? Okay, or previously, people does not have computers, so you can plot it into the chart. So it's very easy how to use it. So if you know the pressure and also the temperature, okay, so you put a temperature here, and you put a temperature there, and then you make a straight line. Huh? And from this straight line, then you can determine what is the K values. Okay, so you can find this in the example. Okay, please read the examples how they figure this thing out. Okay, and flash calculation. Flash calculation means that The liquid at the pressure equal or greater than its bubble point flashes. Okay, not greater, because like for example your water, like my cup of water, even at the room temperature, what will happen? Some of this water will start to evaporate, even though it is not at boiling point. Okay, right? So we use that consideration for calculations. Okay, so how will be done? Okay, let L be the moles of liquid, right? With a mole fraction of Xi and V to be the mole of vapor, a mole fraction of Yi. Okay, right? So you have L plus V equal to 1, and Zi is the fraction of liquid, and V fraction of vapor plus moles of vapor. Okay, right? So you manipulate this, and then we can get that Yi is equal to this. We include the K values. Okay, right? Remember the K values. What is the K value? Here, right? This is the K value. Okay, right? Equilibrium ratio. Okay, right? So we got the K value here. Okay, right? Over this equation here. And then since Yi summation of all the species is equal to 1, then it should be equal to 1. Right? True, isn't it? Right? So Ki more I Z1 is 1. Now, this is 1. Okay, right? So the initial step, okay. Okay, so for further reading, please go to your book, okay, right? My old books, I'm using chapter 10, okay, right? But go back to your books, and I think the previous, and also please look at the examples. So if you have any question with regard to this lecture, please do not hesitate to ask me, okay, right? But please, please, please do your reading. Okay, right? This is something new. I can explain to you in detail using the videos. Okay, right? Please read and try to understand, and you do have question, please do not hesitate to contact me. Okay, right? So thank you very much, and Assalamualaikum, and hope to see you again. Bye bye.